In this example, we are going to discuss how the supportable load in a shaft scales with its diameter. So to start, we have a shaft or a bar-like looking circular rod, okay, that has torques being applied on either end. And the problem says that the shaft diameter initially is at 0.33 inches and it's able to support 80 foot-pounds of torque. And now it's asking, all right, how much torque would a shaft with a diameter that's larger, 0.46 inches, be able to support in units of Newton meters? So we get to do a little bit of a conversion in addition to the actual ratio. So the math comes from the slides at this point, and later we will go through the physics of why this is. But at this point, what I want us to take away is just that the new torque, or the supportable torque in a shaft, scales with the cube of the diameter. Okay? And so we have a new diameter to the third over an old diameter to the third. And we multiply that times the old diameter. And we can go a little bit further. We can plug in the numbers that we have here. And we see that we have this ratio of the diameters, and the units are going to cancel each other out. And this is the torque that we were initially told that this shaft could support. Once we do this numerical calculation, we get the following, but the answer wants us to reply in units of Newton meters. So we need to do a conversion, and that's what you see here. So 1.4 Newton meters approximately is equal to 1 foot-pound. So the resulting torque in metric units is going to be 293 Newton meters. Just like we've done previously, let's go ahead and open up Colab and show ourselves how we go about handling this type of problem. So we'll go ahead and create a new Colab. Hold on, there you go, right click, more, and we'll call this file supportable load shaft. And when we say load, that could refer to a torque or a force. And it's just kind of a ubiquitous term for whatever we're putting onto our system that it has to withstand. So in this case, we are going to go ahead and do our import of NumPy as NP, and we can go ahead and run that. And I'm going to create a new cell. I like to separate them out. I think a lot of people do. And we're going to put in our T-old, and maybe these look a little bit different. So told, and that was, you might have to go back, but that was 80, whoops, just one equal sign. 80, and sometimes people like to put spaces, so yeah, okay, sure, we'll add spaces. Let's see if I can be consistent. Foot-pounds. So this is just a comment so that we know what those units are. And in this case, I'm going to do dnew. I'm going to define different variables. So dnew is set to be 0.46 inches. Okay, and again, I think it's just helpful to have those units. Wow, this is that smart. It's going to do dold. Now, it wasn't 0.38, but it's 0.33. Okay, I guess I had a different problem where I used that. And I think that's about it. So we'll do a tnew, okay, equal to the told, okay, and asterisk, and then look, okay, so is that the right ratio? No, it's being smart, but it's still not quite exactly what we want. So we can do dnew over dold, and then we do asterisk asterisk 3, not to the 1/3, but to the third. So it's guessing, and that's nice. Okay, and this would give us the answer in units of foot-pounds. But we know that we don't want it in foot-pounds, we want it in Newton meters, so we can do times 1.36. Okay, and that will then give us the answer in Newton meters. We can go ahead and print this result. So in this case, we'll do T new, and you can actually use uh, straight up quotes if you want, but you can also use just hyphen here. And we'll do the mp.round of the T new. Oh, I got rid of it. It was thinking. I think 1 decimal point would be fine, or even 0. We don't have to be super precise. And then I do Newton meter, just like that. Okay, and I think it might give a space, so I don't have to have that space, but you see that I added spaces here in that portion. Okay, and we'll run it. So you can hit Control Enter on a PC, and we get 294.7. All right, and that's pretty close to what I said. I guess when I did the calculation previously, I got, where is it? I got 293 Newton meters. All right, so that's definitely within a percent or so of the same thing. So these are just fine. All right, so that's how you approach this problem. Thank you.